Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see the second part of the module 2, that is column. So first, in this video, what we will see that Euler's column theory, then assumptions in the Euler's column theory, means whatever the assumptions they made while deriving the theory, then type of in conditions, how many types of conditions are possible, and then column with both int. So in this video, we will see these topics. So let's start with the Euler column theory, right? So first, in that, what is that? Failure of a column. So when column can be failure, or what is column, that we will see. So a structural member subjected to an axial compressive force. Just see here, this is in E. That should be the axial, right? Then axial compression. So you see, axial compression. It's not like that axial expansion. Compression force is acting on that one, right? That is called what? A strut. So right now this one is a strut, or that may be like this also. So from here, so these two cases are there where along the axis force is acting. But in that case, if the same strut is vertical, so this is a strut, but here this one is the vertical. So that time we will call this as what? Column. This strut is horizontal. So this is a strut, and if that strut is vertical, then we can say that is the column. So here only is there. Okay. So just here, as per the definition, strut may be horizontal, inclined, or even vertical. In all direction is possible. So vertical, horizontal, and that can be inclined also along this axis. That force can act, right? But the vertical only, but a vertical strut used in building or frames is called the column. So where we will use the vertical one, that only we can say that is the column, right? Now, it has been observed that when a column or a strut is subjected to some compressive force, then the compressive stress induced. So once force will apply, the stress will be there. How we will find that? Sigma equals to P by A, that compressive force divided by cross-sectional area. So sigma equals to P by A, where P is the compressive force and A is the cross-sectional area of the column. The load at which the column just buckles is called buckling load. So before breaking, that's buckle at which it's getting buckled, that is called buckling load or critical load or crippling load. All are same name. So anything, remember all the three. Don't get confused with what is buckling load, what is critical load or crippling load, because once that will reach to the maximum, after that column will break. So that's why it's given as crippling, that critical load also, or crippling load also. Okay. And the column is said to have developed an elastic instability. Just here. So now that becomes unstable. Okay, but because of the elastic property, still they not broken. Still they are just like this is there, right? Here suppose if this fixed, if you are applying the force here, then what happens? This will bend like this, right? So this curve, that from the straight to this curve is called buckling of the, that means buckle, and the load because of which this is got buckled is called the buckling or critical or crippling load. Now, Euler's column theory, the first rational attempt to study the stability of long column. What is the long column? Later we will see in the same, was made by Mr. Euler. So first, for the long column, it's found by Euler. He derived an equation for buckling load of long column based on the bending stresses. So he used the bending stresses formula to derive for the long column. While deriving this equation, the effect of direct stresses neglected. Earlier also we had seen what? Only, that means shear stress should not be there, only the vertical, that is axial load, should be acted on that one. So if any shear stress is there, that need to neglect. Euler's formula cannot be used in the case of short column. So this formula is not applicable for short column because the direct stress is considerable and hence cannot be neglected. So in short column, this we cannot neglect. But in long column, the direct stress we can neglect. So that's why this is not applicable for the short column. Next, some assumptions are there for Euler's column. Based on that only he derived. And these assumptions are very important. Sometimes when in exam also they are asking, write down the assumptions made by Euler for the Euler column theory. Okay, so let's see. The following simplification, just to simplify, that means instead of complicating, just to simplify whatever the assumptions he made. The following simplifying assumptions are made in the Euler's column theory. The first one, initially the column is perfectly straight and the load applied is truly axial. So see, if already the curve is this one, curve is like this, and then again if you will apply the buckle, then it will get buckle like this, then it's difficult to find from here to here how much it will get buckled. So that's why, just for simplifying, he said no, that in starting we have to assume this line, the column is straight. After applying the load, only it's got buckled. Okay, that is the first assumptions. And load also is acting truly axially, not even 1 degree aligned or at inclined 1 degree. So truly that it's axial along the axis of that beam will pass, that on that it's acting. Second assumption was the cross section of the column is uniform throughout its length. So throughout from here to here, that cross section should be uniform. It's not like that from to here this much is there and from here to here is thin. No, then again it will be difficult to find. So that's why uniform cross section. Third one, the column material is perfectly elastic. So this material must be perfectly elastic, homogeneous and isotropic, and thus obey Hooke's law. So this column should obey the Hooke's law also. That is for elastic. The length of column is very large as compared to its cross-sectional dimension. So whatever this cross-sectional dimension will be there, from that it should be very large. So from here only the one concept came, that slenderness ratio. That slenderness ratio that we will see later, it's the ratio of diameter to the length of the column. Okay, next was the shortening of column due to direct compression being very small is neglected. So because of this, what happened? This will get compressed, right? This at this end. So that we are neglecting because we are considering only the crippling, that is buckling. So whatever the compression is there, that also is neglected. The failure of column occurs due to buckling alone, due to not this compression, that we assume whatever that failure of column will be there, that is just because of the buckling alone, not by the compression, direct compression. Okay, then also he assumed some sign convention. So first sign convention is what? A moment, which tends to bend the column with convexity towards its initial center line as shown in the figure, right? So this is, if this is there, then we can say this as positive. Means if this is the initial line and it's bending towards this like this, then we can say this is positive. And if this and bending like this, so this is a straight one, and if it's bending like this, then we can say this is a negative one. So a moment which tends to bend the column with a concavity towards its initial. So this is almost, you can say, convexity, and this is the concave mirror, right? So this is convexity, and that convexity is taken as negative. So this is the sign convention that you have to remember. We will use this sign convention while deriving the end condition formula. Okay, so next, types of end condition of column. Okay, so in actual practice there are a number of end condition for column, but we shall study the Euler's column theory on the following 4 types of end condition which are important from the subject point of view. So we will see only here 4 end condition, okay, for your syllabus. So what is the first one? Both end hinged. Both end hinged means what? Here also is there, and this is here. So this is not fixed, it's hinged. Second one, both end fixed. So now second one, this end is also fixed, this end is also fixed. Third one is end fixed and the other is hinged. So one end is fixed and another one is hinged. Third one is fixed and another is free. So one end is free and another is free. So now force is this, we have to see all the 4 conditions. Okay, now just see one by one. So in this video we will see only one condition. Next video we will see the next conditions. So first, column with both end hinged. Just here I showed you the figure. So this is the hinge. So after applying the load P at B, this got buckled. Let's assume, just here. Okay, just see first. Consider a column AB of length L. So this length is L, hinged at both the ends A and B, and carrying a critical load at B. So at B, critical load is there as a result of loading. Next, the column deflects into a curve from A x1B, right? A x1B, or sorry, A x1B. as shown in figure. So this is bent like this. Now let P equals to critical load on the column, just Y deflection of the column at X. So from here at a point A, you can take from the B. No, just because at B force is acting. So here we are taking from A at a distance X, right? What is the moment? That is, sorry, what is deflection? That is Y. So once we will find for this one, then we will integrate from 0 to L, we will get the total value, right? So now just see here, deflection of the column at X. Moment due to the critical load P. P will be what? P equals to, let's see here, this is concavity. Concavity moment is negative. So that's why P force and how much deflection is there? That is Y. So P into Y is the moment. Now just apply the bending moment equation. So EI d2y by dx square equals to M. That is the moment equation. So what is M here? Right? So M is minus Py. Just substitute here. So on, let's see, this is the moment EI d2y by dx square equals to M. So what we have, M equals to minus Py, just substitute here. After substituting, this is the value. Now bring this to this side. So this becomes EI d2y by dx square plus Py equals to 0, right? Or just see here, this term, for solving this differential equation, the coefficient of this should be always unity. So what we will do, divide EI with each term. So after dividing EI, what happened? This EI will get cancelled and here this will be EI equals to 0. So can we write this as d2y by dx square plus P by EI, this constant term, and Y equals to 0. So just in simpler way we wrote. Clear? As you see, it's written minus sign due to concavity towards initial center. So this is the concave one. So that's why that is the minus sign. So now what we will do, we require the solution of this one. So that already we had seen the solution in mathematics. Solution of this differential equation is what this is. So the general solution of the above differential equation is what? Y equals to A cos x root P by EI plus B sin x root P by EI. So just see how you will remember. This Pi, whatever is there with Y, that will be inside the root. Yeah, Py. And x is there, so x. So A cos x root P by EI plus B sin x root P by EI. Now here what we have to do, that is A and B is what? Constant of integration. Right? For that, we require to find the value of A and B. For finding A and B, what we will do? We will use the IND condition. So, or you can say the boundary condition. So, let's see here, where A and B are the constant of integration. We know that when x equals to 0, right, y is equals to 0. So, let's see here, in this figure. At here, x will be what? At 0 here. So, at x equals to 0, what happened? Any deflection is there? No. Means y also will be 0. Similarly, at x equals to L, at this point, there is no deflection. But at a small x equals to this value, then deflection is y. Okay, so we will use this boundary condition. So see, at x equals to 0, y equals to 0. So after substituting here, let's substitute here. So y equals to, I'm substituting here, that boundary condition. So y equals to 0. 0 equals to A into cos x is 0. So 0 into root P by EI plus B sin 0 into root P by EI. 0 into this 0, that is equals 0 equals to A cos 0 plus this will be again B sin 0. Sin 0 is how much? 0. So 0 into B, 0. So this total term will be 0. Now cos 0 is 1. So 0 equals to A into cos 1. Cos 0 is 1 plus B sin 0 is 0. So from here what we will get? A equals to 0. Okay. Now we have A equals to 0. Okay. Next, again boundary condition, we will use another boundary condition, but just I showed you same, just to find this one. So similarly, at x equals to L, y equals to 0. So let's put that value. So now we will substitute A here. So first substitute A. So now what we have, y equals to 0 into this term will be 0. So just writing this term only. So y equals to B sin x into root P by EI. Okay, this is now after substituting the value of a. What is the condition next? X equals to L, y equals to 0. So put x equals to L here. So y is 0 equals to b sine L root p by ei. Now just see here. Either b will be 0 or sine this will be 0. If b will be 0, then already a also we got 0, then we cannot integrate. So means, let's see here. A little consideration, this we got, right? A little consideration will show that either b is equal to 0 or sine this value is equals to 0. Now if we consider b to be equal to 0, then it indicates that column has not bent at all. If b also is 0, already a is 0, means it's not bent, means definitely b is not 0. So what is 0? Then sine of L root p by ei is 0. Okay, so now what we can write this as? So from here we have to find this one. So sine L root p by ei is equals to 0. So instead of 0, can we write this as sine pi or sine 0 sine pi sine 2 pi so on, right? So instead of taking 0, this whole thing will be 0, we will take this as sine pi, right? So we can write this as sine L root p by ei equals to sine pi. So from both sides we can remove the sign. So from here we can write L into root p by ei equals to pi. Now what we have to find? P. So for p is square root, so squaring both sides. Squaring both sides. So what we will get? L square into p by ei equals to pi. So from here p equals to, pi square. So p equals to pi square ei by what? L square. Let's see here. We got p equals to pi square ei by L square. Okay. So see, I am once again recalling this whole thing, right? So this is just a statement or just assumptions. These assumptions are there before derivation of the Euler's theory, or for Euler's column theory. These derivations they made. That is just for simplifying the numerical question. Okay. Then sign convention will be, if it's a convex type, then it's positive. If it's concave type, it's negative. Next, these are the conditions, right? Many conditions are there, but according to your syllabus, these 4 conditions are there, right? So one by one derivation for each, that means one by one we will see all the derivations. So first we will see both in hinged, right? So both in hinged is A and B is hinged. So it's a given just A B column. So now A and B, that this column is hinged. So initially it was this. After applying the load P, that got buckled, that beam got buckled. Okay. So now we have to find how much it's buckled, or that value of P for which it's got buckled. That P value we have to find. Right. For that, what we will do? First, we will find the moment equation. So from this moment equation is what? M equals to minus Py. Why minus? Because it's concave, right? And for concave, according to sign convention, it's a minus y. What is the bending moment equation? Ei d2y dx square equals to m. So after substituting m, you will get this one. Now take this to this side. So after this, ei d2y dx square plus py equals to 0. Now for simplifying this, right now we cannot simplify this differential equation. So for simplifying, the coefficient of d2y dx square should be unity. Means what? After dividing by ei, we can make it unity. So just divide by ei both the both term. Means by the in the both or for both terms. So this will be what? d2y dx square, ei will get cancelled, and here p by ei into y. Now the differential equation of this will be what? Here. So y equals to a cos x root p by ei plus b sin x root p by ei. Now here a and b is what? Integration constant, means we have to find that value of a and b. For finding the value of a and b, what we will do? We will use the boundary condition. So what is boundary condition here? We are seeing at x equals to 0 there is no deflection. Similarly at x equals to L there is no deflection. So at x equals to 0 y also will be 0. At x equals to L, y also will be 0. That condition we will use. So in first case, when x equals to 0, y equals to 0. After putting in this one, what we will get? A cos 0 into this one will be 0. B sin 0 into this one, 0. So sin 0 is 0. So B will get over. From here, A cos 0 is what? 1. So A into 1 equals to 0. So from here, A is 0. So once we have A is 0, substitute here. So this whole term will be 0. Now for the next boundary condition, what is there? Y equals to B sin x root P by EI. Second boundary condition is what? When x equals to L, y equals to 0. Substitute. After substituting, what you will get? Y is 0. So 0 equals to B sin L root P by EI. Second boundary condition here. Now already we have A 0. If B also just here, so either B should be 0 or this sin L root P by EI should be 0. So if B will be 0, means already A is 0, B is also 0, means that will vanish. We will not get the solution. So for that, definitely L root P by EI is equals to 0. So just put that sin L root P by EI as 0. So sin L root P by EI equals to 0. For 0, let's see, we have to find from here. So we have to remove this sign. So 0 can we write as what? Sin 0, sin pi, sin 2 pi. So both sides, sin, remove it. Then from this side, L root P by EI. 0 we cannot take because if from 0 you will take P also will be 0. Right. So now at pi. So this one, L root P by EI equals to pi. Just here it's written least significant value. So after squaring both sides, find P. Okay, just square both sides. So after squaring both sides, it will be L square into P by EI equals to pi square. So P one side, take all other sides. So P equals to pi square EI by L square. Okay, so this is the derivation for both end hinge condition. In next video, we will see the other boundary, that is other condition like both in fixed, one in fixed, other hinged, one in is fixed and the other free. Okay. So in this video, if you have any doubt, or just see here is the reference where you will get these derivations. Okay. So you can refer that book also, or you can just refer, and if you have any doubt, you can just comment down the comment box so that I can give you or I can explain your doubt, or if you have any doubt, you can directly contact me for your clarification. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.